Alright, and one of the last things we want to look at is the idea of center of mass. Because the center of mass is the average position, or the average mass-weighted position of particles. So what we can look at is we can say that the x center of mass is going to be the sum of particle A and its position plus particle B and its position, and so on to the ith particle, divided by the total mass. This is where the idea of weighted averages come from, is this physics concept works its way into other mathematics. And so you add up all the mass. The idea would be, if you take something like a ruler and you position objects around a pivot point, like a seesaw, and you were to add up all the masses and divide 5 kilograms here, 10 kilograms here, 2 here. The center, or the balance point, would be the place that balances out the center of mass. And so the center of mass links itself back to momentum uniquely for us. And so we can see that the velocity of the center of the mass would be mass A times VA. So the velocity of the center of mass. So if a whole bunch of particles moving, then the particle velocities will have a velocity center of mass. Especially if there's no external forces coming about, there's a central velocity of all these particles moving together. And so these ideas come together, which means that there's a total momentum in terms of the center of mass. So I have a collection of particles moving, and there is a center of mass here. That center of mass has a velocity. The center will move. Even though all these particles are spreading out, the balanced center will stay the same. And that center of mass will conserve momentum. And so we can talk about the momentum of the center of mass is equal to the momentum of each individual particle, summed together. Whoops. A, E, and B, and so on, up to the ith component. And so this is the total momentum of a system. Well, that meets the definition we were using before. We added up the momentum of everything in the system, but what we have now is we can treat this system as moving in one. It tends to get used a lot. Let's say I have a rocket that goes up and it's moving in this direction with its mass and its velocity. And at this point it explodes. And so its particles move off in all directions. But if I track the center of all of these particles, it will continue to move following the center of mass. Even though the particles spread out around it, their center is still back at this initial momentum. And the conservation of momentum will keep the center of mass moving even though the particles themselves are spreading out. And the motion of the center of mass is neat. When things move, the center of mass is the part that we track coming across. Let's look at one of my favorite viewpoints of the center of mass. This is something I think from a kid I noticed and never understood the effect until I learned the physics of it. But if you have a boat and you have a heavier person sitting on the boat, we'll say 80 kilograms, and a lighter person sitting on the boat, 50 kilograms, so like a grandfather and their grandson, and they're fishing. And so the center of mass, if we make this the 0 position here, then 0 times 50, and we'll say and so let's see, we'll make it 100 meter, not 100 meters, what's a good boat size? A good boat size will be 10 meters, 5 meters. 5 meters. And so this will have 400 kilograms times 5 meters. And this will have 50 kilograms times 0. But you add them together and you get 400 kilograms divided by 130. Right, we're trying to find our center of mass, and so we do the division. Go back to our equation list here. So what we're trying to do is the center of mass is the sum of these times their position, and I want to put this on position 0, and this is 5 meters away. This is going to be 400 kilogram meters divided by 130, because that's the sum of the two. And so 400 divided by 130 goes into there, 3 times 390. And so 0, so 3.07, so about 3 meters. And so the center of mass is here. About 3 meters. Now, if they were to stand up and walk to the other side of the boat slowly, so that the shift, the center of mass would move on the boat to be 2 meters over here. Right, we could redo the calculation, figure out where everyone's at, but the center of mass would shift, because this would be the 0 point, the 80's on the 0 point, and so we get 250 divided by 130, which is approximately 2 meters. And so the center of mass from the boat frame will switch. But because I'm not adding any momentum to the system, standing from the shore, when they switch on sides of the boat's going to shift forward, so that the center of mass that was on 3 it's going to shift in the opposite direction. It's going to shift forward a meter this way, because initially the center of mass was here, by the water. When they move, the center of mass moves back to here. But because there's no momentum, this position of the boat has to line up with this position in the water, if the boat shifts forward a bit. And it's this center of mass and how the momentum is conserved with it that we see objects shifting when we shift objects coming across. And so we find our center of mass by taking the mass times the position and dividing it by the total mass for each particle. And we'll use summation notation. And we note that a velocity center of mass is the sum of each velocity's particle divided by its mass, and our total momentum is each particle times its velocity of the system. Momentum is still conserved. even when these systems rotate themselves. And the boat example, I hope, is one that you visualize. All right, we'll continue to work on some example problems. Email me if you have any questions.